Welcome viewers. Today we shall be discussing on the module 35, which is on heteroscedasticity part 1. As we have noted that in the OLS methodology, the assumptions of the error term in terms of the OLS assumptions needs to be perfect. Like in terms of the assumptions of the error term, the most important assumption is that the variance of the residuals should not vary with the observations, or the variance must be constant. But if there is a violation of these assumptions or violations of this particular assumption of constant variance, then we invite the problem of heteroscedasticity. So this term has two components. One is edasticity, which means the variance, and hetero means which is keeping on changing. See, if the variance of the residuals vary with the number of observations or it keeps on changing, then this problem is encountered in the data set. And as a result of this, the OLS methodology will not be applicable. This boils down to the concept of or the meaning of heteroscedasticity. So we actually proceed for what is meant by heteroscedasticity in this particular context. So as we can see that the variance of the residuals is non-constant or it keeps on changing with the number of observations. So if we deal with a multiple regression model or a bivariate regression model where there is one independent variable or more than one independent variables to affect the dependent variable, then in running the regression, we may find out the residual series, and the variance of the residual series is keeping on varying with the number of observations. So as we can see that heteroscedasticity results in an unequal scatter of the residuals. So as mentioned in the slide, unequal scatter of residuals means residuals are clustered at a particular point of time or at a particular point of observations, and that is how we can see that the variants are changing and it is following a pattern. And if this pattern is highly pronounced, then the variance is not constant. So we go by the particular expression that variance of error term is sigma square I. Because I refers to the ith observation which is running from 1 to n, and if this I changes and if the variance also changes equally, then we can see that the problem of heteroscedasticity is there in the data set and we cannot apply the normal properties of the OLS estimators. This actually refers to the concept of heteroscedasticity, and based on the concept we can identify what are the types of heteroscedasticity. Because the problem can be moderate or the problem can be severe. If we refer to pure heteroscedasticity, then absolutely the variances are changing and thereby the pattern is being observed. Either the variance is increasing with the number of observations or increasing trend, or the variance is decreasing with the number of observations or a declining trend. So in terms of pure heteroscedasticity, the problem is highly severe. But if it has an impure heteroscedasticity, then it can be due to the model specification error, because there might be some other variables might be included, or there might be some problem of the incorrect number of independent variables that can be sorted out and the problem can be rectified. So whatever is the problem, we are actually dealing with more pronounced in a multiple regression model where independent variables are too high, and so there is a specification problem, or there is a non-specification problem, and accordingly two types of heteroscedasticity can take place. One is pure versus impure. This basically boils down to the problem of representation. That means in the context of the word heteroscedasticity, when the variance is keeping on changing and the residuals is actually showing an increasing or a decreasing order of variance, it is very important to find out the problem graphically. Because in any kind of data analysis, first of all, we go for a scatter plot to identify the nature of the problem, and then we want to confirm that particular pattern with the help of any kind of test, and after that we can go for the rectification. So here we are going to discuss about this particular question, that how can the problem of heteroscedasticity be represented graphically. And for that we invite three cases. Case 1, where we are actually taking the care of OLS assumption and which is being satisfied, that the errors are having constant variance or homoscedasticity is there, so there is no heteroscedasticity. Case 2, the problem is existing and the variance of x is increasing with the increase in the number of observations. So initially, suppose the number of observation is 50, we have a variance of sigma I square. But after that, as I increase the number of observations to 80, the variance is on the rise. That means the variance is getting inflated with the increase in the number of observations, and it is changing. So if this increasing trend is done, then the problem is severe. Similarly, in case 3, we are observing a downward trend, which means with the increase in the number of observations, the heteroscedasticity is on the fall, but it is showing a pattern. So if any such kind of pattern is observed, either decreasing or increasing pattern, then the problem is severe. Otherwise, if no pattern is observed, then the problem is having non-identified or non-existing, and that's the problem of homoscedasticity. So now we move on to the cases one by one. In case 1 in the slide, we observe the problem of non-heteroscedasticity or homoscedasticity is there, which means that as I plot the observations of y against x, which are the scatter plots, and we observe that along the fitted line, the distance between the actual value and the observed value, that follows a bell-shaped distribution. That means this is the plot of the residuals, and the plot of the residuals follow an uniform distribution, and this distribution is bell-shaped, and it is consistent across the lower set of observations as well as for the highest set of observations. So this consistent pattern confirms that the problem of heteroscedasticity is not there, so Euler's assumption is absolutely satisfied. Now we move on to the explanation of the case 1, where we observe that the residuals follow a bell-shaped distribution. Uniform distribution is observed because the variability is same, that means no variability at all, it's constant. And so we can carry on with the OLS and the assumption is valid. We go for case 2. In the case 2, we observe the problem to be existing because at the lower set of observations, the residual plot is showing a bell-shaped, but in the highest set of observations, we observe that this is more skewed and this is more inflated. So as far as the explanation of the case 2 goes, we observe that the distribution of the residual is increasing because it is becoming more inflated with the increase in the number of observations. Variously, the slope is increasing, and so at every point on the fitted line, the distance is on the rise, and thereby the assumption of homoscedasticity stands out to be invalid. So this is a problem of severe heteroscedasticity as reflected in the residuals after the OLS estimation is being conducted. Similarly, we go for the third case where the problem is actually existing but a decreasing trend, because at the lower set of observations there is a pattern, but as the observations is on the rise, then the variance is on the fall, and that is shown by the downward sloping straight line. So in this particular explanation, we observe that the distribution of the residuals, particularly the distribution of the residuals that is falling with the increase in the number of observations, so it is having a negative slope, and the assumption of homoscedasticity stands to be invalid. So that means in the case 2 and case 3, we have the problem of heteroscedasticity to be severe, which needs to be detected and corrected accordingly. But in case 1, the problem of homoscedasticity is existing. And that is how the variance can be constant or can be varying. If it is varying, then the OLS cannot be applied, and that has to be detected by the graphical representation at the initial step. After detecting the problem of heteroscedasticity graphically, it is important to analyze the sources of this problem. Because in the real life data analysis, it is very important to identify what can be the various situations when this problem will be more and more pronounced. So one after the other, we shall be actually analyzing on the sources of the problem of heteroscedasticity when the variance of the residuals is not constant, rather it is changing with the number of observations, either in an increasing manner or in a decreasing manner. So first of all, we look at the problem of heteroscedasticity in a cross-sectional data. Because the data can be of two types, cross-sectional or time series. In case of cross-sectional data, the cross-sections are actually changing, but the data point is fixed, and thereby the problem is actually pronounced. So if we find out the relation between the consumption and the income, then it can vary across different income groups. So if the level of income is on the rise, definitely the level of consumption spending will be rising. Accordingly, the residuals will show an increasing pattern. And for the same type of sample, for the low income groups, the variance will be less for the low income ones because the consumption spending will be less. So for different income levels, we will be observing either an increasing trend or a decreasing trend, and that will be reflected in the residuals. So as far as the first source is concerned, we observe that heteroscedasticity is applicable in case of a cross-sectional data, where the level of residuals or the variance of the residuals will keep on changing across different income groups, and accordingly the consumption pattern will change. Now we go to the second source of heteroscedasticity. The second source says that whenever we are going for any kind of regression exercise, sometimes there is a tendency to take the data in average. This is being done just to actually take care of the fluctuations in the observations. But by collecting the data in the average, there may be some problem of heteroscedasticity in the sample because the average or the mean value is affected by the presence of outliers or the extreme observations, and accordingly the residuals will respond. So again, for the income consumption data or income consumption relationship, the residuals will be on the high for high income groups, it will be on the less for the low income groups. So that means in case of the data analysis, if the observations are taken in the average, this problem may exist or may be finding out. Thirdly, we can see that whenever we are dealing with a kind of a data collection techniques, because the data needs to be collected properly with accuracy, so when we are collecting data through certain techniques, it may actually deal to some kind of impact on the variance. For example, if we deal with a monthly data or a quarterly data, then we will have few errors, and these few errors might be that the heteroscedasticity will be less pronounced. But if we take a data which is actually an annual data, there might be the problem can exist, and thereby the sigma I square is likely to decrease. So depending upon the cross section, and as we shift from cross section to time series, in this transition, there is a possibility that the problem gets eliminated gradually, but it might be non-consistent in a monthly data or a quarterly data, but in annual data it might be present or not, but in cross-section data is very much evident. So whatever be the data collection technique, accordingly the sigma I square will differ. So firstly, in case of the observations where we have different cross-sections, secondly in terms of averaging the data, thirdly in terms of the nature of the frequency of the data collection, the sigma I square will be varying. Fourthly, we come to a very important factor of the discretionary income when people have. Because sometimes the people actually want to spend more or to save more. See, if the person has the habit of spending more, then sigma I square will be definitely be changing frequently. Or if the marginal propensity to save is on the high, then it will be differing. So it will be less. So depending upon the attitude or the personal choice of the individuals, even sigma I square will vary, and this will be more and more reflected in a cross-sectional sample. Similarly, we can also see when people have more choices about their saving behavior. So in the fourth source of the heteroscedasticity, we can see that if the people have a higher tendency to spend, then sigma I square will be on the rise with the rise in the income. But on the other hand, if there is a more provision to save, then it will be less. So in a given sample for a cross-section, sigma I square will be differing according to the choices of the individuals or the pattern of their spending or savings. Similarly, this is the same observation for the companies. The companies may show greater variability in the profits or their dividend policies, or the company may have lower variability in their profits as per their company policy or the rule. So here also, when we collect the data of the companies at a particular point of time, that the cross-section is the company unit, then also the sigma I square will change according to the policy decisions that are taken, and so the variability will keep on changing. So this is about the discretionary power that can be exercised by the individual unit, either it's a household or a firm. Next, we move on to the fifth source, which is because of the presence of outlier. Sometimes we collect the data and where we find out that one or two observations are either very small compared to the others or very large compared to the others. So in this case, the variance will be affected by the presence of these extreme observations, and as a result of that, outlier will be creating this type of problem. In most of the softwares today, firstly the outliers are identified by graphical plots and they are eliminated. Otherwise, if they are kept permanently, then the problem of heteroscedasticity will arise. So exclusion might be possible to eradicate the problem, but as a result of that, presence of outlier is definitely one of the strong sources of this problem of heteroscedasticity of changing variance, as taken by point number 5. And then we have when the regression is not correctly specified. As it is seen in the point number 6, that there may be some expression of omitted variables. For example, demand for a commodity is affected by its own price, but if the other factors are not taken up, like the preference, the price of the other factors, or the taste and fashion statements of the individuals, all these factors affect the demand for a commodity, and if they are not taken up, then it might be seen that omitted variable bias comes in. That means we find out that the residuals will not be having any constant variance. They will be affected by the error term, which the variables are not taken, and thereby the problem will be more pronounced. So this will be very much taken up in the OLS methodology, and the methodology will be inappropriate. And the other two problems refer to the skewness and the incorrect data transformation. So when I talk about the skewness, it means that some of the variables are highly skewed as far as the real life data is concerned. For example, distribution of income. So in any nation, it is seen that there is a huge disparity in the income levels between the rich and the poor. So the distribution is by default skewed. That will definitely give rise to the problem of heteroscedasticity. Similarly for wealth, similarly for the import of education. Because if we deal with the data on education, there also at primary level, secondary level, there is a huge deviation in the disparity levels, and that also will be source of residuals. And sometimes we transform the data according to the different functional forms. We take log linear form, or we take any kind of other transformation ratio form. Sometimes this also leads to changing variances, which is unknowingly. So all these problems are creating a problem of heteroscedasticity in this case. So we can observe that in all these heteroscedasticity problems, the cross-sectional possibilities are very high, where in the cross-sectional we find out that the variances are changing across households, across firms, and the problems are highly pronounced. But in the time series, over the frequency changes, this problem is somewhat mitigated. But whatever be the degree of the heteroscedasticity, it needs to be checked and needs to be corrected, because it has created a large impact on the properties of OLS estimators. So here we basically refer to 9 sources of heteroscedasticity which are mostly applicable for a cross-sectional data. After analyzing the sources of the problem of heteroscedasticity or changing variances in the residuals, it is important to identify why OLS methodology cannot be applicable. That means, what are the consequences of the problem of heteroscedasticity? Because if this problem exists and it is not taken care of, then the OLS estimators will be actually having some differences from their ideal properties. As it is seen that under the assumptions of CLRM, which stands for Classical Linear Regression Model, the OLS coefficient or the ordinary least square coefficient of the estimator's beta hat, as in an equation where we have the beta hat to be the slope coefficient, the beta hat possesses the minimum variance estimator's property, which is referred to as the blue property. So these OLS coefficients are blue in the sense that it is best linear unbiased estimator, best in the sense it has the minimum variance, But in the presence of the heteroscedasticity, this minimum variance will be violated. And thereby the above property will be standing, not only applicable but also the variance will be inflated. So in the presence of this heteroscedasticity, the minimum variance property gets violated, and that will be reflected in the unbiasedness property and also in the variance property. So if we go for the consequences of heteroscedasticity, we shall be referring to a multiple regression model where we observe that a number of independent variables is affecting the dependent variables, and definitely there is a presence of a disturbance term. To apply OLS, the properties of the disturbance term comes in. Then we shall check whether the unbiasedness property is retained or not, and thereby we shall go for checking the minimum variance property. Now in this particular slide, we observe the estimated value of beta hat is unbiased. So in order to proceed for that, we go by the following steps. First of all, we observe that yi is beta xi plus ui, where this yi referred to be the dependent variable for the ith observation. Beta refers to be the slope coefficient of xi, and ui is the error term or the disturbance term. And some of the assumptions are being given of this error term as per the OLS assumptions. The first assumption refers to zero mean assumption, which means expectation of ui equals to 0. Next we have, there is no correlation between the error term of two sets of observations, that is, there is no serial correlation among the errors, so no autocorrelation problem as per the assumption. But for the variance of the error term, that is expectation of ui square, it is sigma square ui, which means that I is in the suffix, which means that with the increase in the number of observations, the variance will be on the rise, or with changing observations, the variance will change. So this is the violation of the heteroscedasticity or the homoscedasticity problem, and the problem of heteroscedasticity comes in. Now we actually go for the deviation of each observation from its mean. So when we look for small yi, then it's capital yi minus y bar. Y bar is the mean of the sample. Xi minus x bar in capital letters, which is taken from the sample mean. And thereby we convert the capital letters to small letters, which are the deviations from their respective means. Now the OLS estimator by default is given by beta hat, which is actually given by summation of xi yi in the numerator divided by summation of xi square. All are in small letters because they are the deviations from the mean. So in place of summation of xi, we keep it as it is, but yi we substitute as beta xi plus ui, because that is how the model is being built up, and the denominator is as it is. Now we divide the entire numerator by the denominator into some parts or into some components. The first component takes care of beta, which is basically the slope coefficient. As we remove the bracket, xi gets multiplied, so we get summation of xi square. In the denominator, we have summation of xi square as usual. Then we divide it into two components plus summation of xi ui, which is divided by summation of xi square. So by removing the bracket, we get two components, and after that we are ending up with beta plus this particular expression, which has to take the care of xi ui relationship. But as we know by the OLS assumption that the independent variables are non-stochastic, that means they have no relation with the error term, or the correlation is 0. So in this particular respect, we can say that beta plus expectation of ui is 0, which is the zero mean assumption. So it boils down to only beta. So we observe that expectation of beta hat is equal to beta, which makes it clear that beta hat is an unbiased estimator of beta. That means beta hat is the true representation from the sample, which must be the true representation of the population parameter beta. So beta hat still remains to be unbiased even in the presence of heteroscedasticity. So in the blue property, we have the alphabet unbiased or U, which is retained even in the presence of changing variance, but in case of the minimum variance property, that is being violated. Because we observe that variance of beta hat in the presence of heteroscedasticity is sigma I square by summation xi square. Summation xi square is the common denominator, but in the numerator we have sigma I square. So this I in the suffix is basically the crux of the problem, because this is referring to the number of observations. So as the number of observations is on the rise or change, sigma I square will be changing. Instead, under the presence of homoscedasticity, it was only sigma square by summation of xi square, which means that the numerator is always constant. So since the variance is changing, it is basically higher or exceeding the variance of beta hat under homoscedasticity. So that means the best property is not retained. So in the presence of heteroscedasticity, the unbiasedness property still exists, but the minimum variance property does not exist because the variance is changing with the number of observations. So in this particular module, we can sum up the various concepts that we have discussed. Firstly, we have discussed on the concept of heteroscedasticity, which means when the variance of the error term is changing, so it requires to be identified and also graphically plotted, and we can rectify the problem. But first of all, we need to detect the degree of the problem, either it is mild or it's severe. Now we can also identify what are the different real life situations when this problem can arise, and this refers mainly to the cross-sectional data. And finally, we look at the consequences of heteroscedasticity, because in the OLS estimators, if this problem is ignored, then definitely we will get the unbiased estimate, but it will not have the minimum variance. So in this particular module, basically we consider about the sources and the consequences, and so the problem needs to be addressed separately with attention.